In classical mechanics, force equals mass times acceleration. If you apply the kinetic force of a high-velocity artillery shell to a standard 165-pound human frame, the math is entirely unforgiving. The target is immediately and violently launched backward. Yet when Diana of Themyscira steps into heavy crossfire, she holds her ground. According to the laws of conservation of momentum, that amount of kinetic energy colliding with that specific mass should turn her into a projectile. To understand how she survives these impacts, we need to run a kinetic stress test on her biomechanics. We are looking past the mythology to examine the hyperdense anatomy operating beneath her skin. Her invulnerability is a highly volatile violation of standard physics, a precise mechanical system that we can systematically pull apart and analyze. Our first stress test examines her effective mass. Diana occupies the exact physical volume of an elite human athlete, but she reacts to impact as if she weighs thousands of times more. Human carbon cells have sparse structural bonds. Diana's cells use heavy isotopes, creating a hyper-compressed structure approaching diamond density. This localized density provides the physical inertia of a mountain while retaining biological flexibility. She bends without snapping, absorbing pressure through extreme internal structural tension. When you scale that up to macro combat, her physical strikes carry unimaginable weight. A single punch delivers the kinetic force of a battleship, concentrated entirely into 5 knuckles. She operates as a walking point mass anomaly, delivering catastrophic force through the sheer, impossible weight condensed into her frame. If her physical density is that extreme, catching a falling commercial vehicle should drive her straight through the asphalt like a nail. The environmental math only balances out if her physiology allows her to dynamically manipulate her own local gravitational constant. We call this mechanism gravitational tethering. When she braces for an impact, her molecular structure locks her physical frame directly to the Earth's center of mass. For a few milliseconds, she effectively weighs as much as the planet itself. To execute that maneuver, she calculates an incoming threat and triggers that downward tether in the microscopic window before a projectile makes contact. Human nerves use chemical transmitters that top out around 268 miles per hour. That is far too slow to track modern ballistics. To compensate, her nervous system functions as a bioplasma superconductor. It fires massive electrical signals down her neural pathways at near light speed. These extreme reflexes allow her to calculate trajectories and anchor her gravity so fast that the violence exploding around her appears to be standing completely still. We push the simulation to its absolute breaking point. We expose this unmoving object to a planetary-level kinetic threat to see where the system finally gives out. The danger lies in kinetic overspill. Because her tissues are hyperdense and perfectly rigid, they cannot crumple, bend, or bruise to bleed off catastrophic energy. If she absorbs a force that exceeds her tethering capacity, the energy has nowhere to dissipate. It ricochets, vibrating violently through her frame. If that internal vibration hits her exact harmonic frequency, the structural tension collapses and the anchor fails. The final result is total molecular decohesion. She wouldn't sustain a wound or a broken bone. The electrical bonds holding her together would instantly fail, causing her form to revert to its base elements, shattering into a cloud of fine particulate matter. Her legendary durability exists in a state of perfect, highly fragile physical tension. The architecture that keeps her safe is exactly what makes her destruction so absolute. Moving the world is a matter of applying force. Standing your ground, knowing a single harmonic failure could return you to the earth, requires carrying a terrifying physical burden and choosing to hold the line anyway.